Astronomers know that the spiral galaxy Andromeda, the largest galaxy near the Milky Way, is moving toward our stellar cluster. In a few billion years, when these two galaxies collide, the process of their merging will begin. However, a recently published study revealed that the star exchange process between the galaxies started much earlier than expected. This discovery sheds light on new aspects of the dynamics of interacting galaxies, according to Universe Today. Contrary to popular belief, stars are not stationary. In fact, they move, but due to the vast distances in space, their movements usually go unnoticed. At the same time, there are hypervelocity stars, some of the fastest objects in our galaxy. These stars travel at speeds of up to 1,000 kilometers per s, much faster than Earth's speed of approximately 30 kilometers per s. The first hypervelocity star was discovered 19 years ago, and since then astronomers have learned that such stars can leave the Milky Way. Stars typically move along orbits around the center of their galaxy. For example, the Sun completes a full revolution around the center of the Milky Way in 220 million years. The reasons behind the ultra-high speed of certain stars are linked to gravitational interactions in binary star systems or with the influence of black holes. A black hole can pull one star, while the other is accelerated and propelled into space at incredible speeds. Hypotheses also suggest that hypervelocity stars may result from a supernova explosion in a binary system or from gravitational interactions between galaxies. To understand the interaction between the Milky Way and Andromeda, scientists conducted a detailed analysis. They began by studying the relative motion of the two galaxies, then modeled the gravitational potential of the system, which describes the acceleration of objects in different points of each galaxy. The next step involved simulating the trajectories of hypervelocity stars. During the study, astronomers calculated the flight trajectories of 18 million such stars. The modeling showed that a number of hypervelocity stars have left the Andromeda galaxy and are heading toward our Milky Way. These stars maintain their initial speed, but some slow down enough to be captured by the gravity of our galaxy. To verify their hypotheses, scientists compared the simulated positions of stars with data from the Gaia Space Telescope. As a result, the distribution of hypervelocity stars predicted by the models matched the observations from Gaia. What is this telescope, and what do we know about it? What are its main differences from others? Gaia is an optical range space telescope from the European Space Agency, ESA, and it is the successor to the Hipparcos project. The main task of the telescope is to create a detailed map of the distribution of stars in our galaxy. It was launched on December 19, 2013, and less than a month after launch, it reached its halo orbit, located 1.5 million kilometers from Earth, near the L2 Lagrange point in the Earth-Sun system. The mission's development took 13 years and cost 740 million euros. Using Gaia data, a 3D map of part of our galaxy was created, indicating coordinates, parallaxes, motion directions, radial velocities, and brightness of nearly 2 billion stars. For many stars, information on multiplicity, photometric variability, and astrophysical parameters was also provided. Additionally, the telescope was expected to discover around 10,000 exoplanets, as well as asteroids and comets, in the solar system. The telescope's main instrument is the largest digital sensor ever created for space missions. It consists of 106 separate CCD matrices, each measuring 4.7 x 6 centimeters, with a total resolution of 938 million pixels. For Kepler, the best of its predecessors, the resolution was 95 million. The physical size of the matrix assembly is 100 by 50 centimeters. Gaia's optical system includes 2 mirror telescopes, each with a primary mirror size of 1.46 by 0.51 meters. Each telescope has 6 mirrors. Both telescopes project images onto a single focal plane, and image separation is achieved through digital processing. Diffraction gratings are used for some of the photodetectors. The telescope scans using several types of rotation. The primary scanning is achieved by rotating around its axis, while both telescopes capture a ring-shaped segment of the sky 0.7 degrees wide. Precession allows this ring segment to be slowly rotated. Due to constant rotation, there are challenges in maintaining communication with Earth. Traditionally used parabolic antennas would require a mechanical drive, which could disrupt the telescope's precision. Therefore, phased array antennas are installed at the end of the device, using electronic beam deflection. The total cost of the project, including the spacecraft, launch services, and ground control, is estimated at €577 million. A €317 million contract for the development and construction of the telescope was signed with EADS Astrium. The cost of subsequent scientific data processing, which will be shared among ESA member countries, amounts to €120 million. Now, let's return to the main question. What could the presence of high-velocity stars from Andromeda reveal, and how might this change our understanding of the Milky Way? The study led scientists to conclude that high-velocity stars from Andromeda could indeed be moving into our Milky Way. While these stars are not in the thousands, astronomers claim they will be detectable. The upcoming collision of galaxies promises to be one of the most spectacular cosmic events, forever altering the appearance of the Milky Way. Stellar systems will be ejected onto new orbits, and bursts of star formation will light up the cosmic darkness. Yet even in such moments, when giants collide, the quiet miracle of starbirth continues in the secluded corners of the galaxy. Where in the Milky Way do stars emerge, and what makes these areas true cradles of new life in the universe? What secrets does the mysterious depth of the star cluster cradle hold? What mysteries does its structure, unique features, and centuries of observations conceal? The scattered star cluster, the Beehive, is located in the constellation Cancer and is one of the closest clusters to Earth. Its distance from our planet is estimated at 550–600 light-years, with a diameter of 25–30 light-years, and an apparent magnitude of +3.7 am, making it visible to the naked eye under dark sky conditions. The cluster contains 10 circumflex 10 stars, with a total mass of about 500 m, and the stars are unevenly distributed by mass. The brightest star is Epsilon Cancer, apparent magnitude +6.3 m, which belongs to Class A and is distinguished by strong metal lines. Also notable is the star TX Cancer, a binary system with eclipsing behavior. Most of the stars are on the main sequence, but some have already left it. Among them are Delta Shield-type variable stars, white dwarfs, and 5 red giants. The cluster also contains several blue straggler stars, a rare phenomenon for such objects. What is the true age of the Beehive cluster, and what cosmic events led to its mysterious formation? The age of the Beehive is estimated to range from 600 to 800 million years, making it comparable in age to the Hyades open cluster. Based on the similarity of their movements and ages, it is assumed that the Beehive and the Hyades formed from the same molecular cloud, which has since dissipated. However, there are differences between the stars in these clusters. For example, there are far fewer X-ray emitting objects among the stars of the Beehive, and the mass distribution of the stars also differs. Due to its brightness, the Beehive has been known to humanity since ancient times. The first written mention of the cluster was made by Aratus of Saul in 260 BCE, although it is believed that knowledge of it dates back even further to the works of Eudoxus of Cnidus, 4th century BCE. In ancient Greek and Roman mythology, the Beehive was associated with the feeding trough from which the stars Gamma and Delta Cancer eat. Before the invention of the telescope, the Beehive was considered a nebula. In the catalogues of Hipparchus, 2nd century BCE, and Johann Bayer, 17th century, the cluster was marked as a nebula, with Bayer's catalogue initially referring to Epsilon Cancer as the entire nebula. The first person to establish the stellar nature of the Beehive was Galileo Galilei. In 1609, using a telescope, he discovered that the cluster consisted of numerous individual stars, more than 40. His discoveries were confirmed by other astronomers, such as Giovanni Battista Hodierna and Simon Marius. In 1769, the Beehive was included in Charles Messier's catalogue of nebulae under the number M44, which aimed to help astronomers distinguish nebulae from comets. What modern discoveries shed light on the mysteries of the Beehive cluster in the context of contemporary research and technology? Modern astronomy continues to actively study the beehive. In 2012, 2 exoplanets were discovered in the cluster, PAR 0201b and PAR 0211b, which became the first known exoplanets around main sequence stars belonging to an open cluster. Prior to this, planets had only been found around giant stars in clusters. PAR 0201b orbits a star of spectral class F, which is hotter and brighter than the Sun. Its mass is 0.54 Jupiter masses, making it less massive but still significant by cosmic standards. The planet completes a full orbit around its star in 4.4 Earth days, indicating its extremely close proximity to the star. Such objects are of interest to scientists because their atmospheres may undergo significant changes due to stellar radiation, providing an opportunity to study atmospheric processes under extreme conditions. Exoplanet PAR 0211b is located 550 light-years from the Sun and was discovered by a team of scientists led by Sam Quinn. PAR 0211b orbits its star with a low eccentricity at a distance of just 0.03 astronomical units, AU. A complete orbit takes only 2 Earth days. Due to the use of the radial velocity method, Doppler method, the radius of the planet could not be determined. However, its mass is estimated to be about twice that of Jupiter, classifying it as a massive gas giant. The discovery of PAR 0211b confirmed the possibility of complex planetary systems existing even in open clusters, which are subjected to more active gravitational dynamics. The number of discovered exoplanets in the beehive continued to grow, and by 2020, 6 exoplanets were known in the cluster. These planets are among the youngest and most well-known. Due to the proximity to Earth and sufficient brightness, the beehive remains a popular observation target for amateur astronomers. Using binoculars, individual stars can be distinguished, and with a telescope of 100 mm aperture, more than 100 stars become visible. The best time to observe the beehive is from February to May, when the constellation Cancer is highest in the sky. Due to the cluster's proximity to the ecliptic, observers sometimes see planets and the Moon pass through the cluster, creating a beautiful astronomical phenomenon. How is the chaotic motion of stars within the galaxy related to their birth in stellar nurseries?